Hi, I'm Dave Wishart, CEO of CoolDry. We really appreciate your taking time to watch this brief video. At CoolDry, we've been working for several years on our mission, which is to revolutionize how the world dries clothes. We've developed a technology which is faster and better, yet uses less energy than any existing product. It's a completely new approach, very different from microwaves or recirculating air heat pumps that have been tried in the past. Today's clothes dryer remains exactly the same as the original 70-year-old patent. It is very inefficient. In fact, 6% of all U.S. residential energy consumption is from clothes dryers. The process takes up to 50% longer than the washing cycle, making multi-load laundry even more of a cumbersome chore for the user. There are no Energy Star ratings, as all brands and models are virtually the same energy efficiency and drying speed. 190-degree Fahrenheit fabric temperatures can cause significant damage, wearing cotton and burning delicates. The lint generated, combined with hot exhaust air, caused 4,500 home fires a year in the United States. In fact, it is the second leading cause of home fires. All of these issues come from the basic process used. The hot airflow both evaporates the moisture and carries it off. Special processes such as wrinkle removal and delicate fabrics are unsatisfactory compromises because a single heated airflow must provide both functions. The same compromises are also contained in the drum design and rotation speed. In comparison, the CoolDry electronic drying process is a radical change. Now, RF energy is used to directly heat the water in the load, while the forced air is a separate process to remove that moisture. The RF energy evaporates the water with very little fabric temperature rise, and the evaporation removal airflow is also at room temperature. Now everything is cool, with much lower lint generation and fabric damage. Now I'd like to introduce John Eisenberg, our Vice President of Engineering, who will cover the technical details of the CoolDry system and present a demonstration of our prototype dryer.
Thanks, Dave. The basic concept of the CoolDry idea is both revolutionary and quite simple. In fact, the initial dryer design was sketched on a single notebook page. In order to optimize the dryer design, it was necessary to measure the RF characteristics of a wide range of fabrics and load sizes. The data obtained made it possible to precisely design the RF and control elements used in the CoolDry system. Before demonstrating the prototype, let me explain how the CoolDry system works. Radio frequency energy generated by the RF power source is sent to the dryer drum. Sensors monitor the RF energy and provide an accurate and direct measurement of clothing moisture content to the system controller. This overcomes a serious flaw of conventional tumble dryers that cannot directly sense load moisture content. The efficient generation of large amounts of RF power at low cost calls for advances in semiconductor technology. CoolDry has developed a unique RF power ASIC ideal for this purpose. A fundamental feature of the CoolDry concept is that the drying process is separated into two parts. RF energy heats the water in the load, causing it to vaporize without significantly raising its temperature. The resulting water vapor is carried away by forced air. RF energy, drum speed, and airflow can now be optimally managed throughout the drying process. Now let me show you the prototype we built to verify our technology. This unassuming aluminum box contains all the elements of the CoolDry system. It is a 1/8 scale prototype of a standard 8 cubic foot capacity home electric dryer. Performance can be readily scaled to that of a full-size machine. Let me now demonstrate the operation of our dryer. Clothing is placed in the drum here. RF power is generated by the 500-watt RF power source at an efficiency of greater than 90%. Power delivered to the clothing load is monitored by an RF watt meter. One of the toughest materials to dry is cotton terry cloth. When spun dry in a washing machine, the water content is typically 40% of the total wet load weight. We will start out with 8 dry terry towels. First, let's weigh the dry towels. The dry weight of the 8 towels is 562 grams, or a bit over a pound. This is about 1/8 of the 8-pound dry load capacity of a typical home electric tumble dryer. Let's throw the towels into a washing machine, then wash and spin dry them. The total weight of the spun dry towels is 917 grams. Thus, the load contains 355 grams of water. Now let's throw the wet terry towels into the prototype and close the front door. The timer is set to 0. Now let's start the dryer. 500 watts is being sent to the clothing load. The drum is spinning, the forced air is on, the timer has been started, and it will take about 35 minutes to completely dry the towels. Now the machine has been running for about 30 minutes. This instrument measures air temperature and humidity. As you can see, the room ambient temperature is 75 degrees Fahrenheit and humidity is 55%, measured away from the dryer's exit airstream. We will now check the dryer's exhaust air. The air temperature is 76 degrees Fahrenheit and the humidity is 85%. Note the very small rise in air temperature. Now the dryer has been running for 35 minutes. RF sensors indicate the load is dry. Let's open the door and shoot an infrared measurement of final load temperature. The load temperature is only 77.1 degrees Fahrenheit, very close to room temperature. The towels seem very dry to the touch, but let's weigh them and see how dry they really are. The total weight of the towels is 567 grams. Thus, the water content of the towels has been reduced from 355 grams to 5 grams. The cool-dry process consumes 731 watts over 35 minutes, or 426 watt-hours of energy. Scaling these results by 8 times yields 3.4 kilowatt-hours that would be consumed by a full-size cool-dry machine. A standard home tumble dryer took 80 minutes to dry an 8-pound load of the same type of terry towels and consumed 7.4 kilowatt-hours in the process. This dryer's load also reached 190 degrees Fahrenheit during its cycle. Thus, the cool-dry machine dried its load over twice as fast, using less than half the electrical energy while raising its load temperature less than 10 degrees Fahrenheit. This performance is what makes cool-dry technology so compelling. Cool-dry has made many test runs with our prototype dryer, with full, partial, and mixed loads of various fabrics. This chart shows a comparison of the energy required to dry equivalent loads using a conventional electric tumble dryer versus the cool-dry system. The dryer loads shown are full and half loads of cotton towels, a full load of light cotton t-shirts, and a full load of polyester women's sleepwear. Cool-dry comes up the winner every time by an average factor of 54%. Here we compare dry times for the same group of dryer loads. Again, cool-dry looks very good, beating the electric tumble dryer by an average of 2.3 times. The maximum fabric temperature rise in all runs was 16 degrees Fahrenheit, far less than the 120 degree or greater rise often encountered with standard electric dryers. Based on often observed problems with microwave ovens, people always ask what happens when metal objects are included in the dryer load. Numerous runs have been done with various fabrics and the variety of metal objects shown. Absolutely no metal heating or fabric damage was observed. I hope that this brief demonstration of cool-dry technology convinces you that our dryer is an exciting, new, and green way to dry clothes. Now Dave will share with you some additional ways that cool-dry brings value to both OEMs and consumers.
Thanks, John. Now I'd like to explain how the cool-dry system integrates into a standard clothes dryer. Much of that existing design is still used. So what do the economics of this implementation look like? First, the heater element is removed. Then the cool-dry electronic system is added. Next, a greater than 100% OEM gross margin markup is added as an incentive for their effort to develop and market this new technology. Finally, the sales channel margin is added. Now this results in a total additional cost of $379 to the consumer. So how long does it take for the consumer to recover this added investment? According to Consumer Reports, the average family in the U.S. uses a clothes dryer 8 times a week. The cool-dry system uses half of the energy of a conventional dryer for all load types and sizes. Thus, based on the current average U.S. electricity rates, the savings will be $96 per year, paying for the added cost in under 4 years. Additional savings could come from a rebate for the first Energy Star rating in the clothes dryer industry. The ready adaptation of the cool-dry system to smart grid could yield another rebate. The electronic system can readily be commanded by a smart meter host to adjust its energy consumption rate. Even at half rate, it would still be as fast as a conventional dryer. This control flexibility is just not possible with standard dryers. CoolDry has filed fundamental patents protecting our technology, including the use of RF energy to dry clothes, efficient transfer of that RF energy to the load, a unique RF power ASIC structure to generate that energy, real-time and direct measurement of load moisture content, adaptive control of the drying process, complete process separation of water evaporation from removal. CoolDry has developed a completely new technology which will revolutionize a mature clothes dryer market. It's green. 50% lower energy consumption is very significant. Yet, consumers will buy it because it is fast and very fabric friendly. And they will justify that purchase on a quick cost return. CoolDry technology is unique and it works. Thank you for watching this video, and we would welcome your feedback.